This talk is about Suricata and OCSF. Who knows in the audience OCSF already? Okay, a couple of people. All right, so good. This will be very new to many of you. And yeah, we are not the first time here. So unfortunately, Sasha can't make it today, but he's in our hearts and hopefully also at Discord. And the talk today will be structured in 3 pieces. We'll first introduce OCSF. We give you a quick primer on what it is. Then we'll show you how you can map your EVE data into OCSF. And then the bonus will be, well, now that the data is normalized in a vendor-agnostic way, you can get a lot of benefits in terms of enrichment, accumulating passive inventory data, etc. So Dominik will go in deep in the technical weeds on the enrichment, and I'll cover the first 2 pieces. Okay, so this is an example of how you process data, not just Suricata data in general nowadays. You have your data coming from multiple types of sources, cloud, network, like Suricata, endpoint. You collect all these different shapes, and really this is where OCSF comes into play. That's where the normalization takes place, so you can actually decouple the data acquisition from the downstream analytics. There's this third layer of enrichment, which adds additional data that you can make more educated decisions, say triage your alerts and findings already there before you make a decision where they actually go, and perhaps perform some inline detection there as well. And so let's first focus on this part, because that's where OCSF comes into play. In the past, everybody who has worked with a SIEM has encountered this. So Splunk has its own common information model. There's Elastic Common Schema. Microsoft has its own one. And yeah, this is kind of over and over a vendor-specific thing. And you probably also have maybe worked in an org where, yeah, you just had a giant Excel sheet that had your custom maps of how fields should be standardized so that you can write detections independent of the data sources. So OCSF stands for the Open Cybersecurity Schema Framework. And it's an attempt by various vendors that, yeah, not necessarily are friends per se and have potentially competing products, but they kind of all recognized the problem and decided, we got to do something about this. Like, this is nuts that every SIEM is re-implementing this over and over. And yeah, we're now living in a world where there's a lot more modularity. We kind of treat these phases of the pipeline independently, especially the data acquisition and the downstream detection. So 2022, the OCSF was founded by IBM, Amazon, Cisco, and a bunch of others. And so it was pretty laughed at initially because it said, oh yeah, it's just +1, right? We know this. In 2023, then there was the 1.0 release, and 2024 is the community is now at 1,000 users. It's growing, and there's a lot of interest from a lot of not just users, but actually vendors adopting this. And some vendors have also expressed very clearly that in the future they will only emit OCSF as part of their products, as the way to producing telemetry. And so in an ideal world, we'll soon see that tools natively produce this. And up to this point, well, us users have kind of the chore of mapping the native format of the tool to OCSF. It's not just a standard for events. It actually comes with a shared object model. So what is a device? What is a piece of malware? And it has these intermediate objects that are nested records in these top-level events. And that makes it a lot more useful, because you can not just standardize on what a piece of information, a piece of activity is, but also what are the things, the entities that are flying around and relevant from a SecOps perspective. It's been designed also to be customized. There's this concept of profiles and extensions. I'm probably can skip that if we have, and get back to it later. But the nice thing is, yeah, you don't have to eat it the way it comes. If need be, you can add your own variants and tweaks. So if you go to schema.ocsf.io, you'll see this, yeah, almost MITRE ATT&CK-like looking matrix And it's just the categorization of different events. There's system activity events, and for us Suricata users, network activity is the primary column of interest. And you can see the schema still has a problem in terms of how it would scale, right? There's hundreds of protocols. Like, do we expect that that column just gets 100 entries? Well, it's unclear yet. So there's some challenges but these are well known and recognized, and the schema is working on it. We've been actively contributing to the schema as well at Tenzir. For example, we've added the community ID field so you can pivot between endpoint and network data. And I'm just going to go a bit deeper now into OCSF, how it works. This looks more intimidating than it is, this slide, but the schema gives you logical types. It doesn't tell you how you have to encode, for example, a timestamp. Should it be a int64 with nanosecond precision? Should it be something else? It just has these logical types, and then that gives the implementer leeway. If you want to choose Avro, Parquet, or JSON, you can have a different representation. So there's some primitive types, and there's some derived types like a port. Yeah, it's a transport layer port, but it's actually represented in integer. Just a semantic alias, if you will. There's different, and there's objects, which are basically structured records. And in these objects, you have attributes. Attributes are the atomic pieces inside an object. And you also have arrays, lists of things. And so OCSF has this giant dictionary it lists basically what every attribute is. Could be a source IP, destination IP, all of these things that kind of describe with the data type, and then you can assemble out of these attributes in so-called event class. The event class is a template for an event, and one specific event class here is the network activity event. Think of it as the Suricata flow log, and it has this source endpoint, the destination endpoint, and a bunch of other fields, which they're called attributes in OCSF speak. And there are actually three types of attributes: required, optional, and recommended. And so this is kind of the verbosity you can tune as a user. You can say, I only want the required ones. But if I want to be more verbose, I take also the others. And so another concept that's important to understand, there's this base event class. It's like the mother of all events. It's present in all events. And when you kind of create a network activity class, you take everything in this base event plus your event class specific attributes, and then you get your actual event class. So this things like timestamp, severity, there's different groups of attributes: classification events, occurrence event like timestamp, then the raw data. If you happen to have, say, the raw syslog for every event, you can stuff it in there. That's optional. And then the primary ones are that actually describe what the thing is. So in OCSF, it's intended for SecOps, has also thought about this concept of enrichment. And in enrichment, there's a couple of ways to do this. On the one hand, you can add overlays, profiles. These profiles go into every event class. I'm not going to go into the details. It's a static way to kind of enhance, augment an existing event. Then there is a enrichments array in the base event class, and that one is just an array of, well, creation time, name, type, probability. We'll show, Dominik shows you in detail how to use that later, but this is how you say if you do a showdown API call and want to get the data in, you just slap it on there in this enrichment array. It's convenient, but it's not for the analyst the best thing, because then downstream the analyst has to disentangle the entire array and, oh God, now what's in there? What do I have to do with this? How do I map this? So it's the poor man's version of supporting enrichment. There's better ways, which we'll show later, and that makes the events a lot more juicy, a lot more useful. Finally, the detection finding is a specific event class that has an evidences array. This is where the whole point that the detection finding is already in OCSF a summary of multiple different events. It's not just like in Suricata where you escalate a regular event into an alert, but it's actually potentially a whole collection of events that led to this detection finding. And so you can add all your stuff in this evidences array. All right, so okay, now that we have a rough understanding of OCSF, let's see how we can map data to it, because that's, for us security users, it's often a painful way. It requires a lot of data plumbing, data wrangling, all these lists and records, and yeah, you don't want to spend all of your time just getting the data in from A to B, but actually do good security work. And so here's an example of a Suricata flow event, and the corresponding OCSF event looks like this. So twice the size. But there's also optional and recommended fields in there, so you could have a small, medium, large version of this event, but it's kind of shows you a little bit what's here. Also state that's useful when you do cross-vendor analysis. So in the base event, we have the metadata field, which says, okay, this log name used to be called flow, it's from Suricata, right? So you can do later when you use that format for also other tools, endpoint tools, well, they don't have product Suricata, but maybe product CrowdStrike in there. And so you can do basically analysis here across tools. Every event has a product-specific UID. This is where we put the flow ID from Suricata. Timestamps, et cetera, durations. These are all computed values, and basically duration is age. So then we have these source endpoint fields, destination endpoint, some connection level information. And you can see it's the same information transposed into a different view. But that's the one that's being used, for example, by Amazon Security Lake, a product already out there for a while, scalable, and Amazon Security Hub, another product, just normalizes all of the alerts into detection findings for your posture management. So OSCSF has gotten a lot of traction in the last 6 months, and it's been used in a lot of products, and a lot of vendors who are building their own data lake are choosing to build this on top of OCSF. And, well, when you start mapping data, you realize, well, yeah, initially you think, oh, it's just mapping field names, right? But it's not that. I mean, first of all, you need to get the data in, parse it from its potentially binary format into something structured, and then you start renaming the fields. A becomes X, for example. But you have to do a lot more usually to get it there. You cannot just have a static map of from and to field names. You got to reshape the data. For example, maybe you need to kind of flatten the arrays in here. Well, here's an array of records, and then maybe that one wants to be flattened. And then it's not just the left-hand side, meaning the schema that may change, but maybe you have to actually also mutate the values. Maybe this needs to be capitalized. Maybe you need to prepend the scheme in the URI so that your IOC matches are afterwards working, right? So there's a lot of standardization and ultimately also constraint validation that is part of mapping. It's more than it looks like. And so at Tenzir, we've been developing an open source language. It's called decoupled. And it's very similar to Prequel. It may not say anything to you, but it's basically a lighter version of SQL. And then there's a bunch of other languages in the same space. That's not too important, but the whole point, what we're trying to do is create a language that makes it easy to transpose the data and, yeah, in the form of the way users already think about the problem, like a pipeline, which is easy to grasp, compared to, say, the nonlinear control flow we have in SQL and more powerful but also declarative languages. And there's the whole point is that this is intended to work for security very well with first-class types for IP addresses, subnets, and functions. I will show you an example in a little bit. But the whole point is like there's a data flow, you have bytes and events, and all you have to do is compose your operators in the way that they mix and match. And once you get that, that's you good to go. So here I'll show a piece of TQL that is mapping the Suricata DNS event to OCSF DNS activity. And so this is a snippet of a pipeline. We'll ignore how the data got in, but what we're doing here is effectively filtering on some schema, calling it Suricata DNS, and what we're doing is we're recreating a new event by transposing it. So, fun fact, TQL is a superset of JSON. Here we just write a record that looks like a JSON record, but we have the ability to reference existing fields from the original record, like source IP and source port from the Suricata field. And everything that doesn't fit in the OCSF events goes into unmapped. Unmapped is the standard compliant way to put data in that doesn't fit in OCSF. So we put the full thing in there initially, and then we drop, when we're done, the stuff that we've mapped already. So that's our approach. And we have this pipeline in depth here in our GitHub repository. The way to really think about this is we only care right now about the transformational aspects, not so much about the source and the sink. We'll get back to that later. And so we have also an in-depth version on how you can do this, how to write these mapping pipelines in our docs. And the open source package that we have for mapping OCSF to Suricata has these types of events already mapped. And this is the decoupled expression that basically shows you what's already there. And if you go to our Tenzir/library repository, you see also the Suricata OCSF package out there. And yeah, we invite everybody to contribute and make this kind of a more complete way to get the data from Suricata usable in OCSF in a variety of contexts. And so I said initially we ignore the data, how the data gets in and out. And so these pipelines that you can write with decoupled, they're more just an OCS mapping pipelines here in the middle. So the way these pipelines work is that you can also use them to onboard the Suricata EVE JSON by reading, say, from a file or a domain socket. And then some of these pipelines, they publish to a topic, and then they say, okay, this is the original Suricata data that got unmodified, publishing that on the Suricata topic. And then I have my set of dozens of pipelines, one per OCSF event each, that map the data and subscribe to this topic. And they republish the data on a new topic called OCSF. So it's then up to the consumer to decide, do I want the original work with original Suricata data? Well, then I'm just going to subscribe to this topic. Or do I want the normalized event stream? Then I'm just start at the OCSF data. So for example, a standard case we see quite frequently is, well, you put a subset here, maybe just the detection findings in your SIM, because that's already out of control and costs are hard to cut. And you take the full raw copy and put that in a low-cost object store in S3. And maybe you want different formats here. So these pipelines can either send the data as JSON or also format it as partition Parquet files. So you can just put them in object storage. So yeah, that's kind of the whole part about the mechanism to get the data into OCSF. And we've been focusing on this part so far. And right now, we're going to look about some of the benefits you can reap that are probably relevant from a use case perspective to a lot of you here and that have to do with enrichment. So I'm going to hand over to Dominik now.
Right. Thank you, Matthias. So yeah, we've heard a lot about enrichment already during the SuriCon. So we want to do enrichment in Tenzir and with Suricata specifically, or with the Suricata map data to OCSF. And in general, if we're talking about enrichment, there are three kinds of enrichments that you can make. The first one, and that's also the one that we're going to focus on for this talk, is in-band enrichment. So you can imagine you get some piece of context, some data that you want to use for enrichment, and you bring it directly to your data pipeline. And then within your data pipeline, you can take that context, you can look up some additional values in there, you can put them into your data, and do that very flexibly and in real time. The second way that you can do this is that you do an out-of-band context. So for example, let's say you have like an HTTP API that you're calling for every single IP address that you're getting, you're making a lookup, and then driving that one further, you can actually take a hybrid approach. What you can do is you can then maybe cache the responses and actually build up like a partial context that has some lifetime that lives directly in your pipeline, so that can make it a bit faster. But for Suricata and like the high log volume that we're seeing with Suricata always, it really makes sense to take a look at in-band context, and that's what we're going to focus on. Within Tenzir, we have taken this context abstraction and have developed three kinds of implementations for it. And this entire thing is pluggable, like many things in Tenzir, so you can actually write your own. But the three that we do have are geo-IP databases, so you can just take libmaxmindDB, and you can go to it, and within your pipeline, for any IP address, for any subnet, for any string that resembles an IP address, you can say, okay, what actually is this? Like, you can get ASN data, you can get coordinates, whatever libmaxmind supports. The second one that we support is Bloom filters. Now these are very well suited for large-scale lookups. Like let's say you have a really ginormous table and you don't want to store all the values in memory, then a Bloom filter allows you to say, could this value be contained? There is a certain false positive ratio to it that you can control, but that is something that you can do and realize with the context. And the third one, that's probably the most simple one to think about, is really a lookup table, where you have some key and you have some corresponding value, and you take a look at the key. And if the key matches, what you do is you enrich with a corresponding value as your context. And this is also what we are going to take a look at for today. So if we're enriching with a context and we're doing that in a pipeline, then there is actually 2 pipelines that are involved with such a context, at least 2 pipelines. So at the top, what we see is a pipeline that uses an operator we call enrich. And enrich, it lives somewhere in the middle of your pipeline. It has data going into it and has data going out of it. And the data that you put into enrich also comes out of enrich. But if there is a hit in the context that you specify, we take the corresponding value from the context, we put it into the data, and then afterwards you can live with your enriched data. The second operation that we support for context is update. So you can, in a separate pipeline, continuously update your context so that you can say, okay, this is not just a static CSV file, some static file that's living somewhere, but instead it's actually a living document over time. And you can, for example, like do an API request every hour to fetch this data, and then always have an up-to-date lookup table for your context. And we will use this, but first of all, I want to highlight the lookup table a bit more specifically because it has actually 3 very exciting features that are a bit special, and that especially for security analysis may be very interesting. So one thing that we built in, Matthias mentioned earlier that Tenzir has a rich type system, so we have native IP address and subnet types, and if you put in as a key for the lookup table a subnet, you actually get CIDR lookups with longest prefix matching for your values. So we have a customer that's using this. They have a set of subnets that they simply specify, and they say, okay, these are my machines, these are my servers, these are my clients, so this is internal, this is external. Specify some ranges in your network, and then for every data that they get out, what they do is they take a look at the source IP addresses and the destination IP addresses, and they just use it to classify. The second option that lookup tables support is per key expiration. So what you can do is you can set 3 kinds of timeouts on every single value that you put into your lookup table. So you could say, okay, this value can live at most for 30 days, for example. Or this value, when it is not refreshed within 14 days, it will expire. Or you can also say this value, when there is no lookup, no enrichment happening for this particular value within 2 days, we will also expire this from the lookup table. And now the third one, and here a small disclaimer, this is coming next week, so this is actually only in dev right now, is that you can do aggregations as part of lookup tables. So you don't just, for the context update pipeline, you don't just take the last event that you put in there for the update as your context, but you can actually specify what you want to have in there and then build up and improve your context over time. So for example, you could have context updates in this form where you have input events that contain a domain and a timestamp, and then when the first event arrives, your lookup table will look like this. It is defined here with some key that's mapped to domain, and then also with 2 timestamps that are specifically specified as the minimum of time and the maximum of time for our context updates. So when you get the first event, okay, this is a new key, we will create an entry in our lookup table. The second one here, badguy.com, that's also a new key, so we will create a new entry in our lookup tables. Now we have 2 in there. Now the third one here, this is actually evil.com again, and this time we have a slightly different timestamp. It's 2 days later. So what's happening now is that we are updating the existing entry, and the minimum of January 1st and January 3rd is still January 1st, but the max that we can now actually update. And then the same happens here for bad guy, where we then update the earlier date so that we over time really have context that we can use for enrichments that is always up to date and that gives us a picture of the data we have processed so far. So how can we do this? The easiest way to do that, to create a context, is just to do it in configuration. You can also create these dynamically. And I want to show this for a lookup table simply. So we'll call this one IP-to-hostname, and you're probably seeing where this is going by now. And we're specifying here a few arguments. These are the aggregation functions that you've been seeing. There's a whole array of them. So like everything basically that you would commonly expect to see in any data frame library for aggregation functions, we should support, and if not, it's pluggable. Open a PR, contribute, it's open source, or tell us, and we'll gladly do it. But you can do a lot of things with this. So in our lookup table here for the IP-to-hostname, we'll simply count how often have I seen this IP address. When have I first seen it? When have I last seen it? Then we also have a field here called evidence. We'll get to that in a second. And we're collecting all the distinct values in a list that we had for evidence. And then lastly, for the host name, we're using an aggregation function called mode here, and mode gives you the most common value over time. So this was simply like, as you update your context, this will give you the host name that you've seen the most for any particular IP address. Now, how do we update the context? And that's, again, where we go into TQL. And we're just getting data in. We're subscribing to the OCSF feed here. We're taking a look at DNS activity events. DNS activity, it contains, you probably also know this all from Suricata, it contains a list of objects called answers. And in that, you have a type field, and that type, it could be A or quad A, and then we can like slightly reshape this into a new event. So we're saying for every single one of these, that's what the unroll does, where we have A or quad A, label the evidence as DNS because this is coming from DNS, take the timestamp from the event, call it seen so that we can use it in the aggregation function that you have seen here. And then going further, we take the host name from the query object and the IP address from the answers object. And then we're updating our IP-to-hostname context and saying, okay, take the key for that from the field IP. And we can repeat this. So now we're doing the same thing again in another pipeline. And we're now doing it for HTTP activity. So we're again updating our IP-to-hostname context. Here for HTTP, what we're doing is we're taking the host name from the HTTP request object. And for the IP address, we're taking here the IP value and the destination endpoint object. We're similarly here labeling the evidence as HTTP. So same thing again, and we can do this again and again and again for all pieces of data. And that's now where the standardization really comes into play, because you now, this is 3 pipelines already, but you just now need to do this for everything that OCSF offers, but you don't need to actually do this for Suricata, for Sophos, for CrowdStrike, for everything basically, right? You don't need to do it over and over again because you just do it on your normalized data once. So here we have it again, network activity for TLS objects. You get the idea by now. So what's in our context when we do this? So we've seen the context definition before. I copied it here into this neat little table. So let's say we got these 4 events here that arrived at the context update. So we had here maybe 2 from the DNS pipeline, 1 from the TLS pipeline, 1 from the HTTP one. And we're seeing different host names, different IP addresses. And then over time, we built up this lookup table that has IP addresses here for the key so that we can use them for the lookup. And we see, okay, how often have we actually seen this? What evidence do we have? And what's actually the most common host name that we've had for this? And this is very valuable information. So now we kind of want to make use of it. And that's, again, another pipeline. Everything really is a pipeline with us. So what we're doing now is we're, again, taking all the detection findings from the OCSF feed, and now we're using the enrich operator. So now we're saying, okay, we want to enrich with our hostname context. We want to enrich on the key source IP, and then a second time here on the destination IP. We want to put this into a field called enrichments as per the OCSF standards, which this is one thing that Matthias said earlier, that there are multiple options for enrichments. One of the fields is the enrichments fields, and the enrichments field is a list of objects that require a certain format. So we'll just say, okay, we want to append into it. The default for this is to override if there is a context. And then lastly, we're saying, okay, actually take the OCSF format, so put in the created timestamp, put in the name of the field that we're matching on, like give it a small little wrapper as a record that looks exactly what OCSF wants to have. And yeah, if we do this, we can see here in our output that for a given detection finding, and this is one that I redacted from a production setup, we had here actually a log coming from Sophos, and this was a detection finding, so some alert from other software, not Suricata, and we were able to enrich it with data that I think actually came from Suricata. So you can see here that we actually had one enrichment. So you see this enrichments array here containing the objects as specified in the enrichment object specification in the OCSF schema. And you can see in here, okay, when was this created? I shortened the timestamps because I redacted the data. You see what field did we match on, what value did that field have, and then also actually the data of the enrichment at the time of the enrichment. Obviously, this data updates over time, but you then get basically the current state of the lookup table at that moment in time. So we can just repeat this over and over and over again, right? So let's do passive MAC. We define a new context. We subscribe to some DHCP activity data. And we're just saying, okay, let's write into that lookup table and let's just write a single value into it, namely the MAC address, if we have it, for a certain IP address. And actually here we're using the write timer to say, okay, this data, if it is not written again within a day, let's just expire it. And then lastly, we can repeat the same thing again. This time here, we're actually using a different option. We are now putting it into a profile, not into the enrichments array, because in OCSF, there's an optional, or I think even recommended field called MAC in the endpoints. And so we're just writing it in there from the context that we had. Now our event is more meaningful than it was before. Now, really, and this is like kind of almost a call to action, it is all of our time to get creative, because we can really now build passive anything with this approach. We've all seen passive DNS, like I don't need to go into how that works, but you could do passive TLS, right? So you can take a look at what certificates do you see per IP or per SNI. So you just take a look at your network activity data and you collect all the distinct fingerprints. You can take a look at JAR4, and actually we wrote a package for this already. You can take a look at HTTP, so for example, you can take a look at user agents per IP address. You can take a look at server software versions. You can take a look at SMB and say, okay, what shares have I seen offered for some IP address? And even Suricata specific, you could take a look at flow statistics, so you could count the distinct source and destination IPs you've seen per connection. And then similarly, do the same thing all over again, but now do it with the number of packets or bytes sent and received. And this really, it's a flexible framework. You can do whatever you want with it, basically. And we are very, very keen to hear your ideas on what you would want to build up passively over time as a database to enrich with. What is the data that you think could be passively collected that you, as an analyst, perhaps, would want to see in your data so that you can more meaningfully work with it? So if you have any ideas there, we want to hear them. And that's it. It's a wrap.
Yeah, questions, please.
Hello, super interesting. I got my usual question on the alert. I tried to look at the code and I did not see how the IP is parsed in the alert. Which one do we take in OCSF?
So alert is actually, there was a long discussion within the OCSF community as well, because the natural way of escalating an event that is an alert is basically the full event plus the alert context, right, in Suricata. So you basically have multiple ways to map this. One way would be to map it to the OCSF detection finding, but then you're discarding basically the metadata. Or the alternative would be to simply map it to, say, DNS activity that triggered the alert, and then you add a mix in, or in OCSF speak, a profile. And I think the base event even now has, since a couple of months, a field called alerted. It's a Boolean, and so it means if some sort of signal fired on it. And so we think that's the better way to do it, because it preserves the metadata, and then you can still just embed the alert data in there. But it's not clear exactly. Like this, it's not as easy.
If you take, for instance, a DNS server where you have hits on the outside, you have information about a bad domain being contacted, but you don't really know. It's not you often, in a lot of cases, don't have a real client, and the server is not on the attacker too. Yes, that's super open.
Yeah. But that's good. So, but the more people engage, and also the more people have this discussion, the more influence we have on the OCSF schema to kind of make that work for Suricata data. So we're already an advocate there, reaching out for Suricata, because a lot of our users are Suricata users, and so I think this will get better over time. And we have some crutches right now, but there's not a canonical way to map an alert to an OCSF event. It's just there's many options, unfortunately.